Hi everyone. So I'm excited today to talk to you about interpolation. So this is lecture 18 on interpolation, and I'm going to go ahead and just dive right in. So we're going to have, just for a quick outline, so we're going to talk about the concept of interpolation first. So I'll write that up here, concept of interpolation. And then in part 2, we're going to do linear interpolation by hand. So linear interpolation by hand, and we'll do this in Excel. And then for part 3, we're going to do interpolation in Python. Okay, so those are the 3 parts of the lecture today. So let's get going. Let's talk about number 1, the concept of interpolation. Okay, oh, look at that line. We're going to get it 3rd time's a charm. All right, there we go. So if you recall, last time we talked about, or in the previous lecture, we talked about fitting. And in fitting we had data. And so interpolation, we're also going to have data. And to lecture today, we're going to compare and contrast interpolation with fitting. So suppose I have some data here. This is my y-axis, this is my x-axis, and I have some points out here. Okay? And this one would maybe be, this one here would be x0, y0, x1, y1, x2, y2, etc. Okay? All right, and in interpolation, we have this set of x sub I, y sub I data. Okay, that's our data. And interpolation, we want to know the value of some y, okay, of x that is not in our set. Okay, so we want to know, we don't know, for instance, what this point is right there. So we know that that's some x, y, okay, but we don't know what y is, and it's not in our set. So, and I'll just say, so interpolation, okay, is when we have some x and y that's not in our set, but x is within our minimum and maximum range here. So, if you look at this range here, this is our x min at x0 and our x max at x4, and the x we care about, is right there. Okay, so it's within the range. That's interpolation. There's also extrapolation. Oh man, spelling today. Extrapolation, which we're not going to talk about. Okay, that's when x is not in that minimum to maximum range. Okay, so if I had tried to get something out here where it wasn't inside the range of my data, that would be extrapolation. All right, so we want to know something that's inside that range. So let's just do an example of this. All right, so suppose you know that it costs $24.80 to fill up your car with gas. Okay, and suppose you also know that you have a 12-gallon tank. Okay, so you have this data point, you have this plot that kind of looks like this, so you know that there's 0 gallons, $0, and you know out here you have 12 gallons, okay, and $24.80. Okay, so the question is, now suppose it's 1/4 full. All right, suppose it's 1/4 full. That means you need to fill 3/4. That's kind of crazy. I think we just had a little earthquake go through. Okay, so suppose you need to fill up 3/4. So you're somewhere here, right? You're at, you need 3/4 times 12 gallons, which is 9 gallons. Is that right? 9 gallons. 12 over 4 is 3. 3 times 3 is 9. Okay, so you need 9 gallons. Okay, how much money is that going to be? All right, so why don't you pause the video and see if you can figure that out real quick. Okay, so if you did that, most of you probably assumed that this was linear between those 2 points. And if you assume it's linear, you're going to get $18.60. Okay, so that is an example of interpolation. All right, so that's just a quick example. So let me sort of back up and explain a few more things. So if you notice that in our example here, and maybe as I've drawn here, usually what you want is some kind of smooth function that goes through all the data. So you might want something, that's smooth, that goes through all of these pieces like this. All right, and so I'm going to write that down. In interpolation, you want smooth functions that go through all of the data. Okay, so a good way to have that is to have piecewise functions. So if you look at this example here, right, where I drew these bunch of points, you sort of intuitively want to put lines through them, or something that's, maybe smooth between 2 or 3 points. All right? And the easiest way to then come up with these piecewise functions is to have piecewise polynomials. Okay, and so there's a couple of reasons why you want to have piecewise polynomials, right? So why polynomials? Okay, two reasons that I can think of. First is they're simple. All right, so you can have linear, you can have lines, you can have quadratic, okay, etc. These are simple things that you can come up with equations for. So you intuitively, know that filling up your gas tank is a linear process, right? And so you intuit, linear polynomial here. In many other processes, it's pretty simple to assume something like a line or something quadratic. All right. The second reason is a mathematical one, and this is called the polynomial uniqueness theorem. Okay, and the polynomial uniqueness theorem basically says that if I have 2 points, I only have one line that can go through them. And if I have 3 points, I can only have one quadratic that can go. Okay, so line, 2 points, line. If I have 3 points, there's a unique quadratic that goes through them, and etc. 4 points, I get 1 cubic. Okay, so this means that I can go back to my data up here, and I can know if I have 2 points, I can make a single line that fits them, or 3 points, a single quadratic, etc. So that theorem makes it easy mathematically. Okay, the other thing you might ask is, well, why piecewise? Okay, if I know this, right, and I have 4 points, why not just fit 1 cubic to, to the data? Or if I have, 20 points, why not fit a 19th order polynomial to that data? And I'm going to show you real quick here some some Python plots just to show you why not. All right, so this isn't meant to be the example that we're going to do. I'll show you another example file later. But let's just look at some plots here to sort of go over this. So if you look at this first piece here, this is just setting up a function and pulling some things in. Okay, so here, I'm going to talk about that one in a minute. Let me get down to, I think it's this one right here. Okay, so let me go back to this for a minute. Okay, so notice here, suppose that this is some function, this dashed line here, is some function that I have data from, all right? And if I just want to fit it with a single point, I have 2 points, I fit it with a line, that doesn't work very well, right? Now I move up to order 2, so now I have a cubic. And now I'm picking 3 points, still doesn't fit it very well. Okay, but what happens if I drastically increase? I go up to 5 points, so that one's a bad example, 6 points, okay? Notice I start to get a lot of oscillations as I try to fit that high order polynomial to all of these different data points that I'm going to fit. If I go up to 8, I get even more wild oscillation. So it seems like I'm doing pretty good in some spots, okay? But if I try and fit this whole, or if I try and interpolate this entire function with something like a 10th order polynomial, I get these really wild up and down oscillations, and that's doing a really terrible job. So I don't want to just use a single polynomial to fit the whole function. It would be better if I had these 8 points and I just put lines in between them than if I put a single 10th order polynomial to fit that. Okay, so why not piecewise is because I get these wild oscillations. Okay, and that actually has a name. That's called Runge's phenomena. So Runge is a German person, German name, Runge's phenomena. And that's how I think the internet says you're supposed to say it. So I don't know Runge personally, but that's how I've understand you should say his name. Okay, so when you're going to do fitting, then what you want is to have some smooth function that are piecewise polynomials. That's a pretty good answer. All right, and so it turns out that that has a name. So a piecewise polynomial, okay, that exactly fits every data point has a name. It is called a spline. Okay, S-P-L-I-N-E, spline. All right, so and there are different orders of splines. So you can have a linear spline. Okay, that would be with linear functions. Okay, linear piecewise functions. Boom, boom, boom. So that would be like this one. You can have a quadratic spline. Okay, that would have second order or quadratics. Okay, and you can also have a cubic spline, which would be third order or cubic equations. Okay, and et cetera, et cetera. You can keep going. All right, so there's a trade-off here. So the linear spline, you're going to get, discontinuous first derivatives, right? But it's pretty simple. In the cubic spline, you're going to get these very nice smooth fits that'll actually have continuous, first and second order derivatives. So, f prime, f double prime will all be continuous. Okay, but it's a little more complicated to construct the cubic spline than to construct the linear spline. All right, the last thing is we need to compare and contrast fitting versus interpolation. At least for the last thing in this conceptual part. All right, so in fitting, so let's put fitting over here and interpolation over here. So in fitting, you have a single equation or a single model. So remember, you had data, you had this noisy data. You'd fit one line through the single thing. Whereas in interpolation, you have piecewise polynomials. So you have lots of equations, right? You've equation, cutting everything, okay? Usually in fitting, this is physically informed. Okay? So there's usually some, it really is a model, right? So we had this equation last time that was x is equal to vt, all right? Interpolation is almost always purely empirical. Okay? Fitting, you have noisy data. Okay, so you've got data that's all over the place, and you accept error, and you're trying to find the best fit line through that error. In interpolation, you want smooth data. Okay, so you've got a plot, you've got this point, that point, and you're going to exactly go through those points, and you want smooth. If you have something that looks really noisy, like this, and you're trying to interpolate, you're going to get a crazy interpolation function, right? So usually you want smooth data. And then this one, again, fitting is an approximate fit, whereas interpolation is an exact fit. Okay, so it goes through every point. Okay, this one doesn't go through maybe any points, only some or no points. Does it actually go through points? Okay, so that's fitting versus interpolation. And I have another example to show you of that here in this Python just to look at. So here is a plot where I fit. So notice, I'm taking this function that I want to fit. I have a bunch of data. It's got all this noise, right? And I'm trying to situate that function just right so it sits right at the place where it minimizes the error. That's what we talked about last time. Okay? But when I'm doing fitting, what I'm doing instead is I have just the few points, and I'm going to make, and here I'm taking my points exactly from this curve. And if I wanted to fit that curve, but I only knew about the blue points, I have these red lines in between them, and that would be a linear interpolation. And that's all I can know, right? That's all I can know about that. So you notice this is linear. I can change the order of interpolation here and make it quadratic, for instance. And you see that quadratic does a better job of getting the smooth curves. And I can even bump that up to cubic, and what we're going to learn next is how to do this. All right? And you can see cubic does a great job of fitting that function. Okay, so here's some practice to see if you can understand the difference between fitting and interpolation. See if you can answer these questions. I'll scroll down and tell you the answers in just a second. So question 1, so suppose you're measuring the heat capacity as a function of temperature. Okay, so you're making this measurement, and you get out some data from your heat capacity measurement. Which are you going to use, fitting or interpolation, to get the parameters to this equation? C sub p as a function of temperature is a times t cubed plus b times t squared plus c times t plus d. Which are you doing? Is this fitting or interpolation? All right, pause the video, and then I'll tell you the answer. Okay, which was it? It's fitting. Okay, so think about this. In C sub p versus t, when you do data collection, you're going to get noise out. And you have a single model that you're trying to fit, and you want to know what are the parameters in that model. This might be physically motivated. It might not be. In this case, I don't think it is. But it might be physically motivated, and you're trying to say, what are these coefficients in this model going to be? So that's fitting. Okay? Question 2 is, suppose that you have a heat capacity data that you measured in question 1, and you measured that data at regular intervals of 10 Kelvin. So you have one at 273, 283, 293, etc. What are you going to use? Which technique, fitting or interpolation, are you going to do to get the heat capacity at 288 Kelvin? Which one are you going to use, fitting or interpolation? Okay, pause the video. Think about your answer. Okay, so now this was a trick question. The answer is it could be either. Okay, if you made this measurement and you really had nice smooth data, you could use interpolation. All right, so if you had data points at 273, 283, 293, and you wanted to know it at 288, you could fit a cubic equation in between there, right? You could do cubics or a quadratic spline or something, right? And you could pull out 288. But you could also go back and make a fit using this formula from above and then just plug in 288 and get out your answer. So it sort of depends on how noisy your data is. You could actually do both. All right, so it's kind of a trick question, but I wanted you to be able to sort of think about that distinction, because this is where it's going to come up in real life. Do I use interpolation if I have smooth data, if I just have a few data points and I want to go exactly between them? Okay, but if I have a bunch of noisy data, then I'm probably gonna fit it. Okay, and I'm going to have a single model and I'm going to do least squares. All right. So I think that's all I have to say about the concepts. So look, we have one more section here. Oop, before I get off of this screen, I went the wrong way. One more section here to do on the paper before we move on to Python examples. So the last little bit here is interpolation by hand. Oop, hit the eraser. Interpolation by hand and by Excel. Okay, this will be, the Excel part will be really quick. All right, so you should, we're going to learn, oh, I'm going to turn that off real quick. Okay, so we are going to learn linear interpolation. Okay, so, and part of the reason we're going to do this by hand is because Excel, okay, has no interpolation functions. Okay, which is a bummer. So we have to at least, but it's okay, linear interpolation is not that hard. So think about this. I've got two data points here. I've got x0, y0, x1, y1, and I want to have a linear interpolation between those 2 points. So I'm going to suppose this is my other point here, x, comma, y, that I want to interpolate at. Right? So how do I go about finding, so usually you're given x0, x1, you're given y0, y1, and you're told x, and you want to find y. So how do you do this? What you do is you say, in the linear case, I know that the slope at this point, and the slope at this point, and the slope at this point are all equal. So the slope between here and here and here and here have to be equal. It's a line after all, it just has one slope. So you can set those slopes equal. You do y minus y0 divided by x minus x0. That must be equal to y1 minus y0 divided by x1 minus x0. Right? So that says the slope from y to y0, this slope right here, right, has to be equal to the whole slope along the whole thing. Right? So that's equal slopes. Right? And now you just rearrange and solve for y, because that's the thing you want to know. So that's the one equation you know. Now you just have to rearrange and solve. So multiply this thing over. So I'm going to have y minus y0. This is just algebra from here on out. I have x minus x0 multiplied by y1 minus y0 divided by x1 minus x0. Okay? And add y0 to the other side. So I have y is equal to y0 plus x minus x0 multiplied by this slope, y1 minus y0 divided by x1 minus x0. Okay, this is perfectly acceptable, but people often rearrange this in a different way to get rid of, let's see, I can't remember, just to show it in a different way. So this one's fine, okay, this is happy, you can do this if you want to find y. But people often rewrite this by multiplying this guy here by a quantity of 1, which is x1 minus x0 divided by x1 minus x0. So I can do that. This is algebra. I'm just going to multiply that in there. Now I have y0 times x1 minus x0. Notice that that has the same denominator. So now I have y0 multiplied by, let's see, x1 minus x0 divided by x1 minus x0 plus, and now I have x times y1 minus y0 divided by x1 minus x0 minus, and I have x0 times y1 minus y0 divided by x1 minus x0. And let's see, did I expand the wrong thing? I totally expanded the wrong thing. Let me back up a little bit. I didn't want to expand this one. I wanted to expand this one because there's a y0 right there. So I want to do the following. You see how I have this quantity? Sorry, I messed up the algebra. This one I want to pull out. So I want to have y1 times x minus x0 divided by x1 minus x0 minus y0 times x minus x0 divided by x1 minus x0. Okay, so now notice I have this piece has a y1 in front of it. This has a y0. This also has y0. Same denominator. Okay, so I can get rid of the x. Let's see. Yeah, I can get rid of the x0, right? Because I have minus x0 minus y0 x0. So I can get rid of that piece. So I end up with y0 times x1 minus x divided by x1 minus x0 plus y1 times x minus x0 divided by x1 minus x0. All right, so what this, so this is the end formula you always see for linear interpolation. Okay, so here is the things I know, here's the thing I don't know. All right, and notice what's nice about this is a weighted average between y0 and y1, right? So I have y0 and y1. Those are the 2 points for y, and then I'm going to average them by these weights, okay? And these weights are related to the total distance of x. So x1 minus x0, that's that distance here. So that's x1 minus x0. And it says I add up the y0 with the distance from x1 to x. So I use this distance here as a weight. And then I add up y1 with the distance from x to x0. All right? So I use the opposite side. This is sometimes called the lever rule. Okay, you're going to use it again in thermo. Just so you know, it's a little preview of what's going to happen in thermo. All right, so we can use this formula to go back and do our example from the very first page. Example from page 1. Okay, so remember I said, we had x0 was equal to 0 and y0 was equal to $0. Remember, I'm filling up the gas tank, and I said x1, that was a full gas tank, was 12 gallons, and y1 was equal to $24.80. Okay, and I said, what happens if we're going to fill up 3/4 full? So 3/4 times 12 gallons gives me 9 gallons. All right, so now I can just take this, plug this into my formula. So I'm going to let you go ahead and do that because I don't want to take the time to do algebra. But if you do that, you'll see you put in, say, 12 here. Well, maybe I will do it because why not? It's not that fast. So I say y is equal to, y0 is $0. So this whole piece is going to go away, but let's plug it in just to be thorough. 12 gallons minus 9 gallons. 12 was x1, 9, and then I'm going to divide by x1 minus x0. x1 minus x0 is 12. So you see how this is the distance on the one side, okay? Plus y1 is 2480, and this one is going to be multiplied by x, which is 0, minus x0, which is, excuse me, x is not 0. X is 9 gallons. X0 is 0, divided by the same 12. All right? So this one goes away. That's 0. And this one gives me $24.80 times 3/4. Right? So 3/4 times $24.80, which gives me the value of 1860, which is the thing that we had before. All right? So there's a little example using this. So now I have an example of doing linear interpolation in Excel, and I'm just going to give you this example. I'm not going to spend time going over it, all right? But essentially what you do is I have this x data and y data, and suppose I want to interpolate in between these 2 points, right? So I have x is 2.5. So to do linear interpolation, I just have to code in, hard code that linear interpolation function between those 2 points, and I'm going to get out the value of y that's somewhere in between those 2 y data points. All right, so I'm using the same formula that I had in the previous thing that I did by hand. I just now have to code it into Excel. All right, so I'll let you spend some time looking through that, and if I remember right, there's a homework problem using Excel, so hopefully that helps you out. Okay, so I'm going to go up here then. We've done 1, we've done 2. Let's finish with part 3, which is interpolation in Python. All right. So in Python, we are going to use a new module. So we've used scipy before, and we've used scipy.optimize. Remember, we use scipy.optimize for 3 things now. We've used scipy.optimize for root finding. We've used scipy.optimize for minimize, for doing optimization. I'm just going to, I think it was the minimize function. And we've also used it for curve fit. Okay. Now we're going to use the scipy.interpolate module. All right. And lucky enough, we're doing interpolation, so hopefully it makes sense that we have an interpolation module. And the function that we care about is called interp1d. So I find that interpolates long enough when we actually are only going to need that one function, that you can just import the module from scipy.interpolate, import interp1d. Then you have the interp1d function. Okay, and so what you do if you're given some data, all right, so here's my x and y data, and maybe it's useful to plot that data to show you what it looks like. Okay, so here's what a plot of that data looks like, so from some complicated function. And to interpolate, what you do is you call interp1d, and you give it the x and y data. That's all you need to do is give it the x and y data. What it returns is a function. So it returns a function that you can evaluate. So if I put in here, if I put f linear, if you look down here at what it says, it's a function. So I can call f linear on any value of x that I want. So if I want to call f linear of 3, it's going to return a number that's the interpolated function at, the interpolated value at 3, which in this case is 0.43. So up here, I could call f linear at 5, okay? And that's going to give me near -1, which is down here, okay? Near where I had before. So this interpolation, interp1d returns a function. So then if I just want to get at a simple value, at this intermediate value 1.5, which is what I'm plotting with the green x up here, I just evaluate it, that function, at that value. Notice that the name that I assign here is the name of the function. So this is just like if I were to do def f linear x whatever, okay, and then have coded in the linear interpolation. All right. I can also, it makes it really easy if I want, I can get a whole bunch of of the functions. Okay, so I could, well, maybe I'll talk about that in a second. But so I can get a lot of points in between. All right. What I'm just doing here with this orange line is I've just plotted, a line in between them. So it's actually, doing linear interpolation in the background to plot it. But it's just putting a line in between those 2 points. And you can see that my linear interpolation function gives me a value that's on that line. Okay. So in addition to doing linear interpolation, this interp1d also will give me quadratic or cubic types of interpolation. So I can run this piece here. And what I'm showing you is that if I call interp1d, if I don't give it anything, it automatically does linear. But if I put a comma kind equals cubic, it will give me a cubic interpolation. Or I can say kind equals quadratic, okay, and it will give me a quadratic interpolation. Okay, so cubic will give me that third order. And now what I'm plotting here is what I was sort of alluding to before. This plot is pretty small. Maybe I can make it, let me see, fig size, let's make it 10 by 8. Let's see if that helps a little bit, making this thing bigger. Okay, so what you can see is that I made my x values a linearly spaced array going from 0 to 10. So it's actually doing linear interpolation along the whole domain of that function, okay, along the whole domain of this data that I've given it. And so when I plot f linear, let me just look at what's going on here. So the data are these blue points, and linear, what I'm doing is now I'm going along the whole space. So in the previous example, I just collected one value up there. But now here, I'm going along the whole space. And so xx is this whole long array where it's evaluating at 0 and 0.2 and 0.4, etc. I can probably make them exact if I change that. Let's see, xx. Yeah, 0, 0.4, 0.8, 1.2, etc. So it's going all along that distance, all right? And now if I change, instead of plotting the linear, I can plot the cubic spline, all right? And now you can see it's this nice function, that's smooth, that goes in between those points, all right? If I want, I can say, I had a function before that I was drawing this data from, and I can put that exact function up, and you can see how the cubic spline compares to the exact values. And notice that it does pretty well here when things aren't changing too quickly, but over here, the cubic spline sort of fails pretty good because I don't have an extra data point over there. All right. So if I have more data points, if instead of just 8 points, I put in 12 points to sample from that function, I do better than I did before. But where it's the most variable, up and down, up and down, up and down, right, where it varies very quickly, I have the hardest time. Okay. So what I'd like you to do, sort of for your last practice here, is to load the data file. And I think it's actually not called lecture 13. I'll fix that in the example I'll give you. It's called lecture 18 data. Lecture 18 data.csv or something like this. Okay. See if you can load this data and plot the data and then put a linear interpolation and a cubic spline and see if you can get the value of y at x equals 2.5. Okay, and down here there's the answer of how to do that. Okay, don't look until you've done it, but there's the key all the way at the bottom so that you can practice and then see what your answer is. All right, so that's interpolation. So just to sort of quickly review what we've talked about, we said, just zooming back out, we said interpolation is a case where you want to know something in the middle of the data that you have. All right, extrapolation was something when you want to know it way outside, but we're just doing in the middle. And we said we're going to do that by fitting piecewise polynomials because they're simple and we can fit an exact polynomial between just a couple points, and it avoids this Runge's phenomena where we get wild oscillations. And we said that interpolation was different than fitting because we did these piecewise polynomials and we wanted smooth fits as opposed to fitting where we had a single model for a bunch of noisy data. And then we learned how to do linear interpolation. So we said, well, we have a simple way to do this. We have just a line which we can set up with slopes. And it turns out that cubic and quadratic splines use similar kinds of things. You say, well, I want to make the slopes equal, and I want to make the first derivatives equal, et cetera, and that's how you end up getting those. And it's just more complicated algebra, but it's still just algebra. And you could follow it. It's just kind of messy and annoying. All right. And we did an example of doing that by hand and showed, hey, we can code that in Excel too. And finally, he said, well, how do we do this in Python? Python will do it for us. We can do both linear interpolation and other interpolation without having to code it by hand. And we said we need to use scipy.interpolate, and we need to use the function interp1d. So they had a function, oh, I don't have my pen on me, so used interp1d. And we called interp1d, and it returned a function that we could then use to evaluate at a single point or at a whole bunch of points if we wanted to do that. All right? So that's interpolation. I hope that was helpful to you, and I hope it helps you with your homework. And we will see you next time.